This is the overview of Chapter 8, the Independent Samples t-test. So the Independent Samples t-test has some similarities and some differences from the Paired Samples t-test. So we're going to start by looking at these. So first off, where we were in Chapter 7b was the Paired Samples t-test. And in that case, you'll remember we would have two columns of scores that we named X1 and X2. And those scores represented pairs that went together. We had repeated measures, before and after scores, for example, where each individual had two scores. We had matched pairs. We had natural pairs like mother-daughter. And it looked something like this. Each individual in sample 1 in that first column of scores was directly paired to one individual in the second pair. So they had something going on. Either it was the same person with two scores, or it was these pairs that were matched one-to-one between the two columns. In the independent samples t-test, it might kind of look the same because we still have two columns of scores, but they represent totally different individuals. So maybe like one group of people receives the medicine and the second group of people receives the placebo, the fake medicine, to see if the medicine is effective. And so it kind of looks the same, right? Because we have two samples. But you can see that the samples are totally independent. They're totally different people in sample 1 and sample 2. We couldn't match each person from sample 1 to a person in sample 2 because there are more people in sample 2. So sometimes there aren't even the same number of people in each condition. So these two samples are completely independent. There's no systematic relationship between them. So what are the differences among the tests we've studied so far? Well, way back in Chapter 5, you'll recall that we studied the z-test, the first statistical test that you learned about. And in that test, we had problems that had one column of scores. And we named that column X, and that was just one sample, one group of people. And we compared this mean for this group to a general population in which the mean was known, and it was labeled as mu, and the standard deviation was known and labeled as sigma. Then we went on to the one sample t-test, in that we had one column of scores, X, and one sample once again, so just the same as the z-test. But in this case, we were comparing the mean for that group of people, that sample, to a general population with a known mean, but an unknown standard deviation. So we had to estimate the standard deviation from the variance of the sample. Then we went on to the paired samples t-test, and in that test we had two columns of scores for each individual, or each pair of individuals. But in any case, whether it was a pair of individuals that were related or each individual with two scores, we had column X1 and column X2, two scores per each individual. And we compared the difference between those scores. We calculated the difference for each individual. We calculated a different score, and we compared the mean difference score for the entire group to a general population that had a mean of 0, no difference between the pairs of scores. And we estimated the variance in the same way as we did for the one sample t-test. And now we're beginning the independent samples t-test. And in this test, we're still going to have two columns of scores, X1 and X2, like we did in the paired samples t-test. But in this case, those two columns of scores will represent totally different individuals. There will be no systematic relationship between the first column of scores and the second column of scores, so totally different people. And we're going to compare not the difference between each pair of scores because we don't have pairs, but the difference between the two means for these two separate samples to a general population with mu equals 0, no difference between means. So we'll look at this a little more closely. So on this slide, I've made a little bit of a flow chart for you so you can kind of have a process for determining what test to use. So first off, you're going to begin by asking this first question: how many columns of scores are there? So do you have one column of scores or two, what's going on. So you're going to begin right over here. And then you're going to go on and answer that question. So if there's one column, then you'll follow that trajectory. If there's two columns, you'll go that way. And so if you say it's one column, then you're going to ask yourself, does the problem give the population mean and the standard deviation sigma? Is that information listed in the problem? And if the answer is yes, then you're going to conduct a z-test. And if the answer is no, it's a one-sample t-test. And so that is the distinction between those two. And so if you answer way here at the beginning that there's two columns, then you're going to follow through and ask, are there two scores per individual, like before-after scores? So each individual person has two scores. And if the answer is yes, then you have a paired samples t-test. And if the answer is no, then you ask yourself, is each score in the first column paired with one score in the second column, as in mother-daughter, father-son, husband-wife? And if that answer is yes, then again, you have the paired samples t-test. But if the answer is no, these are totally separate groups of individuals, then you have the independent samples t-test. So maybe this will be helpful to you as you work through these kinds of problems, and you'll have to do this on the final exam, so this might be a helpful tool for you to hang on to. So here we'll try some of these problems out. So you're going to just be asking which test for the examples given below, and the answer should be a paired samples t-test, a one-sample t-test, or independent samples t-test. Here's the first problem. A researcher randomly assigns a group of 25 unemployed workers to receive a new job skills program and 24 other workers to receive the standard job skills program, and then measures how well they all do on a job skills test. So you can notice a couple things about this problem. First off, you have two totally different groups of people. You have this group of 25 unemployed workers who are going to receive this job program, and 24 other workers. So these are clearly two columns of data, two different groups of people. And because they're totally different groups of people, we know that we're going to have an independent samples t-test. And we see that each worker here, each unemployed worker here, is not in any way matched systematically to these 24 other workers. And in fact, we don't even have the same number in each sample, 25 in one, 24 in the other. So we know they're not paired. So the only answer is an independent samples t-test. Next, a researcher measures self-esteem in 21 students before and after taking a difficult exam. So here we can see we have one sort of group. We have these 21 students, but for each individual we have two scores. So we're going to have a column of before scores and a column of after scores. But each of the scores in the before column are going to be directly linked to a score in the after column because each student is going to have a before and an after score. So this is a paired samples t-test because we have two data points per individual. Each student has a before and an after score. Problem 3. A researcher tests reaction time of each member of a group of 14 individuals twice, once in a very hot room and once while in a normal temperature room. Interesting. So here we have 14 individuals, but next we have to ask ourselves, how many columns of data? How many scores per individual? And so we have one score for each person in a very hot room, and then another score for each person while in a normal temperature room. So 2 scores per person. And whenever we have this kind of situation, we know it's again a paired samples t-test. 2 data points per person, 2 columns of data. Next, a researcher compares the number of potholes on Navajo Nation roadways in 2023 with a number of potholes on Navajo Nation roadways in general. And mu is known, sigma is unknown. And so in this case, we do have, we're comparing one sample, right? The potholes on and roadways. So we actually have each roadway is going to have a number of potholes on it. So one sample, and we're comparing it with the number on roadways in general. And the big kicker here is that sigma is unknown. If sigma was known, it would be a z-test, but because it's unknown, we have a one sample t-test. Finally, Dr. Barsa compared liking for video games between teenage boys and teenage girls. And we can see here that we have two different groups of people. We have teenage boys and teenage girls. There's nothing here to indicate that these are matched in any way, that they're like boyfriend, girlfriend, or anything like that. We think they're totally independent groups, and because of that, we do an independent samples t-test. So I hope this is helpful. There'll be a few more examples when you get to the practice. So one more example of where we've been and where we're going. So remember, once again, in Chapter 7b, the paired samples t-test, we did these two examples. In the first one, we did attractiveness self-ratings, and it was before and after, I believe, a beauty filter was in place. And so we can see here we have two columns of data, x1 and x2, but we have two data points per individual, so only 6 individuals, each person producing 2 scores. And then you'll remember that we calculated the difference, 2 minus 5 equals 3, negative 3, and we did that for each one of these. And then we calculated the mean of these different scores, and we used this for all of our calculations. Likewise, another example, we have pairs of individuals, and the pairs are related. Each father is related to his or own son. We have x1 and x2, but we have these pairs. So we have pair 1 has 2 scores, pair 2 has 2 scores. We calculated the difference again, 20 minus 26, and we did that for each one of these. We calculated the mean of these scores, the mean difference score, and we use that to compare to the general population. So this is what you would see for the setup for a paired samples t-test. Now, the independent samples t-test. Now, the independent samples t-test is going to look more like this. So this is a problem we'll work through in a subsequent slide, but we're looking at this kind of question. Do people who write about traumatic events have different levels of physical health than people who write about a neutral event? Use 0.05 significance level to test the hypothesis. So see what the data looks like here. Here we have 6 clerks, right? And each clerk has 1 score. We might name this X1, but each clerk only has 1 score. Now we have 5 totally different clerks, and each one of them also has a score, but there's no systematic relationship between these clerks. These are just 2 separate groups of individuals. And so what we have to do in this case is we have to calculate the sum of squares for this group. We have to calculate the mean for this group. We have to calculate the number for this group, the degrees of freedom for this group. So we'll go on and get the data for each group, and then we do the same here. The sum of squares for this group, the mean for this group, the number in this group sample, because it's often they're different, sometimes they're the same, and then the degrees of freedom for this group. And once we calculate all that, we're going to use information from both of these samples to calculate the estimated variance. And we'll use information from both of these samples to calculate the variance for the distribution of means. And so this is sort of a framework of what a problem in the independent samples t-test will look like. So whereas in the paired samples t-test, we were comparing the different scores for pairs of scores. So we calculated the difference, and then we compared those differences, the average of those differences, with a mu equals 0. Now we're comparing differences between two means. So we might have, like in our last example, we might have the set of clerks in the first sample, and they might have a distribution that's something like this, and this might be that mean. Now we have a second sample, and that also has a mean. And it's this difference right here, the difference between these two means, which is what we're comparing to a comparison distribution with no difference between these two means. So in the comparison distribution, in this new kind of t-test, the independent samples t-test, we are still going to have a comparison distribution that we're using, but it represents the difference between means. Should have a plural there. And so we're going to have a hypothetical distribution that we imagine like this. So imagine your scientist. I didn't make a little image here, but let's imagine our scientist. We'll have this magnifying glass represent our scientist. And he or she is trying to figure out what happens if we just take a big old population of people and we draw out a sample of, let's say, 5 and another random sample of 5. We figure out the mean for each groups. We calculate the difference. We subtract mean 1 minus mean 2. We toss them back in. We grab another sample of 5 and another sample of 5. And again, we calculate the means. We subtract one mean from the other. We throw them back in. And we do this for an infinite number of times. What do we get? Well, we have no reason to think there's going to be any kind of a difference between these two groups. There's nothing systematic that happened that's different. And so we assume then that there is no difference between the means, and that's what we compare our sample mean to. So let's think about it like this then. Here's that population. And now let's picture that we've drawn a mean out of it, a sample out of this first group. In this case, the mean of this particular sample is 15. The mean of this sample is 16. We subtract one from the other, and we have a difference between means of -1. Here's our scientist. Let's draw. And this is the distribution of the difference between those means. And then we've done this for an infinite number of times. So there's another sample. Second sample we drew, the first one had a mean of 16, the second one had a mean of 16. The difference between the two is 0. We plot it. And we do this again and again. And here we have a mean that's, mean 1 is 18, mean 2 is 14. We calculate the difference, and we end up with a difference of 4, which we subsequently plot. And so this is how we imagine the comparison distribution. If we continued this to infinity again and again and again, then we would end up with mean difference between these two means being 0. So the difference between means, and that's a little different than the mean difference that we worked with in our last chapter. So here we're calculating the difference between these two means. Calculate the means first and then subtract, instead of subtracting each score from another score. So in other words, our new comparison distribution is a distribution of difference between means. And we already went through all that, but let's look at it one more way, because this is how your book is conceptualizing it. So now, remember, every time we draw a sample, and so down on the bottom here we have sample, right? These are the actual data that we got from the people we gathered. They're a little bit different, okay? And we calculate a mean for each sample, and we subtract mean 1 minus mean 2. Whichever way we go, it doesn't make that much difference. And then we compare it to this hypothetical distribution. But remember, whenever we do inferential statistics, we're trying to generalize to a population. So we have these two distribution of means, and this is just indicated because remember, the distribution of means is skinnier than the distribution of individuals. So we have to divide by n. So that's what this is representing. We divide by n to get that little skinnier distribution. We do this for both samples. And then what we're trying to generalize to is a population. So in that example we gave a few slides ago, maybe this population is people who wrote about their trauma. And this is a population of people who wrote about something neutral. And so that's what we're trying to generalize to. So I'm not sure if this was helpful or not, but this is how your book presents it. So I wanted to show you this image as well. So what does this comparison distribution look like in that step 2, which is always the big time-consuming one? Well, this is what it looks like. So first off, it's going to have a mean mu equals 0. You're already used to this because that's the same mu that we had in our chapter 7b. There's no difference between the sample means. So we're comparing it to a hypothetical population where there's no difference between the means, that scientists who drew them out and plotted them all endlessly, and in the end, if we average it out, there's no difference. The shape, once again, is the t-distribution. So we're having, the reason it's a t-distribution is because we're estimating the variance of the comparison distribution from the samples. And the spread, we're using, again, the standard deviation for the distribution of difference between means, not mean difference, but we'll just call the standard deviation for the distribution of means. And in fact, I'll even cross that off to make it easier. This S, again, means standard deviation, but estimated. And this little m just means the distribution of means. So we're doing that skinnier distribution based on the number in the sample. So here is a little bit of, again, a look at all of the tests that we've used. So in the z-test, the very first step, we had the mean for the sample of individuals compared to a population with known mean and known standard deviation. The comparison distribution shape and center, the shape was z-distribution normal, and the center was mu, whatever was given in the problem. And the spread we calculated using sigma for the distribution of means, just the square root of variance divided by n. Then we went on and we did the one sample t-test. And in this test, we once again were comparing the mean for one sample of individuals with a population with a known mean mu given in the problem, but unknown standard deviation. We had to use the t-distribution normal and based on degrees of freedom, and the mu would be given in the problem. But the spread we had to estimate based on the distribution of means. And so we referred to it in brief as EVAR divided by n. And you recall that going back to the standard deviation, we calculated it by dividing sum of squares by degrees of freedom. Next, we had the paired samples t-test. And here we were comparing, again, the mean, but we were comparing the mean difference because we were calculating the difference between each pair of scores, finding out the mean. And so we write it here as the sum of the person's second score, their after score, minus their first score. And then we divided all that by n to get the average or the mean difference score. And we compared it to a mu difference, and it was always 0. Because if we just drew 2 random people out of the population, but didn't do anything to them in between, we just got a before score and an after score, but nothing happened in the middle. If we figured out the difference between their first score and their second score, some would do better the second time, some would do worse the second time, but they'd end up on average with a mean difference score of 0. Here we have the shape t-distribution normal, center is 0, and we estimated the standard deviation in the same way. So this and this is the same. now we're here where we are for this. And so we're looking at now comparing the difference between two means. So we're comparing the difference between those two means. So M is going to represent that, the mean for the second sample minus the mean for the first sample. And we're comparing that to a mean that's equal to 0. No difference between the means in two randomly drawn samples. The shape is normal. Here's the center again. And the spread is very similar. You'll see here we have the square root of E var divided by n, and here we're going to have the square root of what we call E var pooled divided by n, and that's just a variance that takes advantage of the information from both of the two samples. So this is sort of a boring slide. Maybe it will be helpful if you understood our formulas well. So in the one sample t-test and paired samples t-test, we calculated E var by taking SS divided by DF. We calculated VARM by taking the estimated variance divided by n. And then we calculated the standard deviation by taking the square root of VARM. So you can see this is step by step. We calculate E var, and we use E var to calculate VARM. We calculate VARM, and we use it to figure out the standard deviation. Now we're going to have some differences. So in the independent samples t-test, we're still going to calculate sum of squares, but we're going to do it for each sample. So we have two samples. We're also going to calculate proportions for each sample. And the proportion just means what proportion of the degrees of freedom is corresponding with each sample. So in other words, if one sample has 5 and the other sample has 10, we want to place more weight on the sample that has 10. So that's why we calculate these proportions. Then we're going to calculate the estimated variance with a two-step process. So first we're going to estimate the variance for each sample, SS1 divided by DF1, and then estimated variance for the second sample will be SS2 divided by DF2. And then we're going to use both of those estimated variances to calculate the pooled estimated variance. So we'll take the proportion, which will be something like, say, 25% of the degrees of freedom are in that first sample. We're going to multiply it times the variance for that sample. And let's say 75% of the degrees of freedom are in the second sample. We'll multiply that from the variance from that sample. So we're just placing more weight where we have more scores. So that'll be the first anomaly. Then we're going to calculate VARM also with a two-step process. We're going to calculate the VARM for the first sample by taking this estimated variance pooled, E var pooled, divided by N1, whatever number is in that sample. Then we're going to calculate the VARM for the second sample by taking E var pooled again, dividing it by N2. And then we're going to push those in and figure out VARM overall by adding those two VARMs together. So it seems a little longer, it's a little more complicated, but you'll get the hang of it. And then we do the same as we've done always before. We calculate the standard deviation for the distribution of means by taking the square root of VARM. So it's different, but it's not that different, and everyone can get this. So what other differences do we have? Well, the populations are defined by each group, and so we would describe the hypotheses as the research hypothesis is mu1. Then you state the direction, is it greater than, less than, or not equal to, different from the mu for the second group. And the null hypothesis is mu1 equals mu2. So we can state the hypotheses in that way. I'll give you more examples of that. Then another difference is in step 3. We're going to determine we've already gone through the difference in step 2. So in step 3, we're going to determine the cutoff point just the same, using the t-table in the back of the book, but much more recommended to use our t-score calculator, our online tool. And for degrees of freedom, what do? You have two separate samples. And so what we do is we figure out the degrees of freedom for the first sample, n1 minus 1, degrees of freedom for the second sample, n2 minus 1, and we add them together to get df total. That's what we'll use to figure out the cutoff point. And if you hypothesize that the mean for group 1 will be higher than the mean for group 2, you'll use a one-tailed high test. And the reverse is true if you think M1 is going to be lower. So your hypothesis direction will depend on which group you hypothesize to be higher or lower. And finally, we calculate the t-score using M1 minus M2 divided by SM. And we'll use the very same process, drawing the cutoff point and plotting the mean difference here and determining whether to reject HO. So in summary, this is just an overview. We'll go through lots of examples, but in summary, the independent samples t-test compares mean scores for one group of individuals with mean scores for a different group of individuals. The comparison distribution has a mean, or the center, of 0, meaning there's no difference between the mean scores for each sample. We use the estimated variance from both samples to calculate spread for the comparison distribution. And the t-sample score is calculated by subtracting M1 minus M2 or M2 minus M1 more commonly, and dividing by the standard deviation for the distribution of means. So continue on to go through some practice, and there's little videos for each practice because this is a little bit more of a complex process here.